So
Okay.
Jack, you can take it away.
Very good. Okay. Well, thank you all for coming today. I'm excited to be here to tell you about some of the work I've been doing the last few years with Sergey. The model I want to tell you about today is actually wonderfully simple. So even though it's a string theory, what I'll be writing down is classical mechanics. So I hope it's comfortable to string theorists in the audience, as well as people who do stellar dynamics. What have you? Everyone has classical mechanics hopefully under their belts. Despite the simplicity of the model I'll write down, we think it has some deep lessons to teach us about strings that are interesting in the context of QCD. And at the heart, what I'll be telling you about is a model of dynamic relativistic geometry. That is one way to understand what the string I'll be telling you about is today. And if it's boring, well, there's a light show coming, so just like wait. Okay, so the model I'll tell you about is simple, but is motivated by one of the biggest outstanding mysteries in high energy theory today, or in theory land more generally. And it's been a mystery for about 50 years, and it's also been a long-standing place of fruitful developments. And that is the intersection of strings and string theory and fields. So many things live in this space, but the one I'll be talking about today is the fact that in certain quantum field theories, strings emerge as objects that were not there at the beginning. For instance, in QCD, which we can put on computers nowadays and solve very nicely, if you put in two probe quarks, quark and an anti-quark, and everywhere else is just typical QCD, but we don't have take out all other dynamical fermions. What you see is a collimation in the field strength of the gluonic field. So instead of in electrodynamics, where your field lines spread out spherically in a circle, you get this flux tube, which is what it's called, forms between the two quarks. So this is one way that we understand, or one qualitative way we understand the mechanism of confinement. For instance, if this is a string with some finite tension, it takes energy to pull these two quarks apart. Eventually, this energy is above the barrier for pair creation in our universe, and so that string breaks. Once you pull them too far apart, you get more mesons. And these don't want to live far apart. So this is kind of qualitative understanding of confinement. So there's the fact that we get strings emerging in our quantum field theories that we know and love, and our bread and butter in our standard model. Yes.
Can I get a definition of what a string is? Because like in this QCD example, I would naively call that a flux tube and not a string. So like what
Well, by string, I just mean something that has one space and involves in time. Yeah. So this is very close to being one spatial extent. Of course, it has a little bit of thickness, but we can actually take a limit. This is kind of the setting for a lot of the work Sergey does and has been doing for a while, is that you can take a limit, which is in QCD, we have, of course, it's SU3 in our universe, but we can imagine generalizing to SUN. And when we take this n to infinity, we expect that this string shrinks to zero thickness and really becomes truly one-dimensional. And as a string theory, you could study on its own. So kind of big outstanding question in this field is, what is a string theory? Because so far there's many indications that it's like nothing we know about or how to describe currently. So this is a big open question. Problem with this big open question is very hard. Right? The only way we can study QCD in 4 dimensions is like to put it on a computer and do computer simulations, and that's how we even get this beautiful picture of a flux tube emerging. So the question that started this research project, which is the following.
Can I though ask?
Yes.
That project is not on the way to understanding string theory. That project of, looking at that system in 3+1 dimensions on a computer is understanding QCD. It just there happens to be something that has a one-dimensional geometry in there.
Well, the point is that actually it is expected to be a string theory in some limit. And we don't know exactly how to describe it in our usual language we describe other string theories we know about. So part of the motivation could also be to understand the space of string theories better.
I see, but it's
And this is a
it's
roundabout
a
way to-
string theory that lives in 3+1 dimensions.
Yeah, that's right.
Okay, not
Exactly. Yeah.
not
It's-
like whatever M theory, whatever people talk about when they say sort of string theory
Yeah.
that
Mhm.
explains everything.
Yeah, right. So when I say string theory in this talk, it won't be string theory TM. It will be
I see.
generalized string theory.
Got it. Okay.
But I mean, they're probably related. We just don't know how, or maybe they're. That's a big open question. Okay. So the question that motivated this work is looking for: is there a simple simple theory of a QCD string?
Sorry, maybe just a comment regarding Mike's question. So there have been attempts trying to embed the QCD string in the 10-dimensional superstring theory by doing some complicated compactification. But the result people get is not quite this theory. Sites share some similarities, but it's still different.
Okay. Okay.
But that could just be that people have not tried hard.
Try harder.
Motivational. Okay, but what we're going to do here is not try harder on this problem, but simplify to try harder on a different problem. Okay, so we pull out our theorist toolkit. We want to simplify something. Easiest way to simplify something is to drop dimensions. One of our favorite things to do. Sometimes add dimensions, but more often than not, drop dimensions. This has two consequences immediately. The first is that in 1+1 dimensions, confinement is actually classical. That makes me happy. What do I mean by that? I just mean that Coulomb's law, right? The sphere in 1+1 dimensions is 2 points, one on either side of you. So there's no growing area at distance. So the field doesn't really fall off. So actually, even just in electrodynamics, you'll have confinement between two charges. Okay, that's happy. Bad thing is that you lose a dynamical gluon. This is just because in 1+1 dimensions, you have no transverse dimensions to the direction of the photon, so there's no dynamical gluon. So we fix this by adding back in matter, and so we add what's called an adjoint fermion. So this is just a fermion that's in the same representation as the gluon, and so interacts with the string in the same way a gluon would. And what we get out of this procedure is a theory that goes by the name of Adjoint Qcd 2. Now, this is quite old, has some history. It was studied in the 90s for a bit. They were interested in what we'll see later will correspond to short strings. They were interested in this sort of connection. And actually, this model has come back into the literature for other reasons recently, because at n=0, you get all of these fancy generalized symmetries, which I won't be talking about here, but let you do all these amazing things. And these are the non-invertible symmetries and everything else you may not have heard about. But the point is that it's been studied for a long time. But the question we're going to be asking is a little bit different than what these earlier studies were looking at. We'll be interested in this thing I've depicted here, which is studying the theory on a very long string. What do I mean by that? This theory has, let's see where I want to go. So this theory has n vacua, and they're labeled by boundary charges. So essentially the way to think about it is that you can put boundary conditions at left and right infinity, and you can choose different pairs of these boundary conditions, and these label the different sort of vacuum you can take. Way to understand that in pictures is you put some fundamental quark and you put some anti-fundamental quark, and you send these off to infinity. And so this model we'll be studying is really physics that lives inside this meson. We don't have, these aren't dynamical, so they won't be playing a role otherwise. They just give us boundary conditions and give us a string that stretches across all of space.
Sorry, can I ask a question? If I remember not wrong, in 2 dimensions, we have the Schwinger model, we have the U1 field, and we have fermions, and we have confinement in an abelian theory. Why cannot we have QCD also in 2 dimensions if we can have an abelian gauge field? Why we cannot have a gauge theory? I mean, yes, I understand.
I guess I'm confused by the
answers,
question. This
but-
is you can think of this as a generalization of the Schwinger model.
Schwinger.
Just to non-abelian and
But the action also looks like F mu, like that.
yeah,
How does the action? So
it's QCD, yeah. It's Yang-Mills theory and 1 + 1 dimensions, and you additionally have a fermion, which lives in the adjoint representation.
Okay.
That's all.
Okay. Sorry, I thought that as you said, we need the fermion, that we don't have the gauge field, but no, we have the gauge field and another object.
Well, sorry, it's non-dynamical. The gauge field really will act as a constraint.
Okay.
So we need something to scatter. We're going to end up doing scattering experiments. If you don't have anything to scatter, scattering experiments are very boring. So
Right.
that's why we add them in. Thank you for the question. Yeah. So exactly to this point, we'll be adding in these adjoint fermions. And because they live in the adjoint, we can thread them along this line. So there'll be beads on this string. Picture will look something like this.
Sorry, can I ask for clarification on what you mean by that? Because they're in the adjoint, you can put them along this line.
Yeah, sure. So kind of, well, one way you think of it is we're interested in considering gauge invariant operators. So we need to take some trace and just, if we imagine we're in some like lattice field theory or something, isn't it? We just consider the trace of all these, and then these are the gluon fields. And because the fermion lives in the same representation, we can just add it in to the string, just like it looks, just the same as you would a gluon, for instance. So it can become part of the string that you're talking about. That's what I mean.
I suppose also with adjoint fermions, the string cannot break, right, with fundamental.
Right, yeah, here you can see the string ends on the fundamental and anti-fundamental. If we had them in our theory, then the string would break and fragment. And that's not what we're interested in. Although it's interesting to study that later, but not for now.
What would happen to the endpoints charges? Would they be screened by the dynamical adjoint or not?
That is a very difficult question that has been argued for many years and depends on the mass. Recently, I believe it's, so we'll be interested in the case that the mass is very large. But, and in that case, it's not screened and you do have confinement. But there, I believe the picture is now that when it's massless,
Can be screened,
It
even
can-
though it seems that. it
yes,
does not
it's
have
screened
the
when
right
it's
analysis.
massless.
Well, I mean, it does not have the right triality, you expect that the screening would be if the dynamical quarks are of the same nature of the spectator, and with the adjoint, it's not the case, but nevertheless, there is.
Yeah, it's a very complicated story and it has to do with this generalized symmetries. It's very interesting, for sure.
Conceptually, it's because the mass equal to 0 point is strongly coupled. So this kind of exotic things can happen, even though you don't have adjoint matter, it's screen fundamental.
So we'll be interested in the time evolution of these states, and we'll study this in just some quick words about how we study this. We'll study this in the Hamiltonian formalism. And pick a gauge. If you don't know what this means, it's fine. I'm just saying it for the audience, for those who know, but pick a gauge in which the spatial component of the gauge field is set to 0. And then the only thing that appears in the action is the spatial derivative of the time component. There's no time derivative, and so it's non-dynamical. We can integrate it out. And what we get after this process is we get a theory of interacting fermions. And exactly at weak coupling and only keeping the terms which grow at infinity, we'll be interested in studying the dynamics of the string. And we'll see that that is the only, well, it's the only term that grows at infinity as these particles move apart from each other. The string gets longer, so its effects grow. Keeping only these terms, we get the following Hamiltonian. And what I'm writing down now is really now we've moved from quantum field theory, etc. Now we're in classical mechanics. So hopefully everyone take a deep breath. So this is the Hamiltonian for n particles. We have their kinetic piece. And then we have the following potential term. Okay. For example, this potential for n equals 2 looks like the following. It's a function of Q1 minus Q2. That's what I'll write here. And it's simply Q12 plus absolute value of Q12. And this looks like some potential that's just a ramp. The way kind of to understand where this potential is coming from is that exactly we have this exact picture, or that one up there. So we have a very long string and we have two particles threaded along that string. And when they're in their equilibrium position, we have particle 1 to the left of particle 2. But in the other configuration, we have particle 1 to the right of particle 2, and the string is stretched. It's relatively longer, and so that costs energy. So there's higher potential energy. And one thing I've swept under the rug here, but might be interesting to think about, is that we started with just one type of fermion in theory. But the classical mechanics I wrote down, every single particle is actually distinguishable because there's a string connecting them. Right? I know what the correct, quote unquote, correct order of them is in space. We won't talk about as much here, but this is an important conceptual point, and actually is a consequence of the fact that we took the large n limit earlier. Sort that up a little bit. Another interesting point that we won't delve into here, but is another thing that's interesting to think about, is that this is a classical theory, and yet it looks relativistic. And this is actually something that is special to two dimensions. There's some theorems in higher dimensions that say that any classical mechanical relativistic theory is actually trivial, but in two dimensions, many more interesting things can happen. For instance, this one kind of way to understand why maybe this is okay with relativity is that the force that a particle would experience if you're on either side of this potential only depends on the ordering of the particles in space, and boosts won't change that. So anyways,
classical it's finite. It's not field theory. It's finite phase.
Yeah,
finite dimensional phase.
sure, that's yeah, exactly.
Classical
I'm
mechanics.
considering n particles here. And yeah, exactly. We've also, because we've taken these limits, there's no particle creation, spontaneous pair production along the string or anything like that, which might be important to take into account as we go back to the field theory.
So this might be obvious in the when the whole thing's written down, and but like, does nothing special happen when this string crosses itself, or in particular when these fermions become in the, like, to get in that position they have to cross,
Yeah, that's
but they don't. So like the string between them has to go to zero length.
Yeah,
like,
so there are potentially terms that in this adjoint QCD that govern exactly this point when the quarks get close to each other. These adjoint quarks get close to each other, but we've dropped them in this model. And actually, we'll see that this model by itself is interesting for a number of reasons. And but like, to get back to this adjoint QCD story, those might be corrections that you need to take into account.
Okay, but it's totally okay once you're in that position. The string is in one dimension, but it can
Yeah, so-
cross itself.
Yeah, I should
That's
say
not a
that every
problem.
single time I draw these pictures, I'm extending them in another dimension just so they're easy to read.
Right.
Yeah, they're lying on top of, all these segments are lying on top of each other.
Okay.
But basically, the fact that those terms are suppressed is a consequence of these two conditions: that mass is heavy, and also that n is large. So that would ensure that those terms can be dropped.
Okay.
Another thing that this picture should make clear, hopefully, is that after a certain amount of time, the string is just going to want to pull straight. So actually, all states in this theory look like the following. They start out in state, and then after some complicated dynamics, they go to some out state. Where by in, I mean it's boring going back in time, and out means it's boring going ahead. Okay, but the nice thing about this is now it's not, I don't have to do Monte Carlo simulations or anything. This is just classical mechanics. And so you can put this on a computer. This is what we did maybe 2 years ago now. And you actually find something very interesting happens when you send the mass in this classical Hamiltonian to 0. So we're studying a scattering experiment. So if I plot all the momenta of the particles, we start with some incoming left movers and right movers. They start to cross each other. There's strings that are stretched. There's some complicated dynamics that happens here. But exactly when you send the mass to 0, something kind of amazing happens, because you get something that looks like this. What you find is that the set of initial momenta is the same as the set of final momenta. For normal relativistic scattering, you'd only expect maybe energy and momentum to be conserved. So this is telling you that something interesting is going on behind the scenes. It's what's called an integrable model. There's many more integrals of motion than there normally are. And in some sense, that means that this lives in a special class of models. And the immediate question you ask after seeing this is, what are they? So that will be the second part of the talk, is answering what are these integrals of motion and giving you kind of the picture that makes it all very clear. Because I think the picture is beautiful at the end of the day. Something else interesting happens looking at this Hamiltonian when you send the mass to 0. The kinetic energy, of course, just becomes the sum of absolute values of the momenta. And so you find the equations of motion almost look symmetric. So Q dot is sine of P, and I'll abbreviate this to SI. And PI dot this, where SI I plus 1 likewise is sine. You can make these equations of motion even more symmetric. You let me introduce this variable QA.
Sorry, what's QI comma I plus 1?
Sorry, this is the difference.
Okay.
Because that's what tells you
Yeah.
the order of them, whether they're in order or out of order. So if you allow me to repackage almost all the degrees of freedom like this. Furthermore, package all the signs. One more thing you have to let me do is just add a dummy variable that captures the fact that this is always stretched in this direction. This final is always connected to right infinity, and this first one's always connected to left infinity. So I'll call those, just for convenience, S0, 1, because they make everything look nicer. 2, blah, 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 blah. And if you allow me this rewriting, then actually both equations of motion take the following simple form. So simple.
So why is the conversion seems non-trivial here? Because if I just naively think it's just a classical equation motion, the result is it will obey the momentum conservation.
Sorry, so this fact that the final initial momentum are the same is not true when m is not 0.
So why? I mean, because if we just naively solve the classical, if we just imagine there's a classical particles and they interact with each other, then it will always.
This is a set.
No, it's not true. Yeah, it's only specific models. That's true.
I mean, why?
I
Because
think you're asking about momentum conservation, the total momentum. He's talking about the set.
The set. I'm talking the individual, like the individual numbers come out the same.
okay.
So you sent in 5, 2, -3, 3, whatever. You get the exact same numbers when they scatter back out.
Oh, okay.
Yeah, whatever they are.
Okay. Thank you.
And it's not that they didn't scatter.
No, yeah, of
Right.
course they. I mean, yeah, they. It's you wouldn't think. Yeah, exactly. They did scatter. Right. Actually, you'll see that in just a second. So one of my favorite things about this model, yeah.
Can I ask a question? Just to be sure. So here now you're just studying this model by itself without any connection to the original QCD, the 2D QCD.
Well,
Otherwise, this m goes to 0 limit, what does it mean?
well, so another way to understand
Because
this
you
is
first
like
took the
high
limit.
energy. So you could think also like a high energy scattering limit.
Ah.
So yeah, there's we in the.
So this m goes to 0 limit.
So we're considering something like this.
I see. Okay.
Okay. That's a very simple equation of motion and is very far from the QCD that we started with. That's actually one of my favorite things about it is that the equations of motion at any point, you can tell from here, right, is these are all just zeros and one, or -1s and +1s. And so these are piecewise linear functions of time. Which means that when you put it on a computer, all you're doing is matching lines together. And this is something you can do exactly. And you can actually do it quite quickly. And with this, you can, create all these beautiful movies of the dynamics of this string. And I really wanted to show you one of those, but unfortunately, it's a Blackboard talk. So what I had to do instead is I had to find a way to bring those movies inside the room. And it's so simple that you can actually teach an Arduino to solve the model in real time. So when I flip this switch, see the dynamics of the model play out. This is a slightly different version, of course. This lives on a circle, not on an infinite line. I couldn't fit an infinite line in this room, unfortunately. So you can pass this around if you like. So this is the light show portion of the evening. So
It's got the QR code too.
yeah, exactly. So there's some, I don't know if that QR code works, but I have a website if you want to look at more movies. So every 30 seconds or so, it reinitializes random initial conditions and puts them in starting, like in whatever the initial ordering of them is around the circle is the equilibrium. And kind of one of the fun things I like about watching it for a while is that you can start to see the string that connects them all. And, it's good. Anyway, so what's plotted there are like the adjoint fermions.
This is the closest I got to supervising an experimental project.
Yeah. Exactly. So that was very fun. I had a good time making that. Also, go to the makerspace. You all have access to it. NYU makerspace. Like, it's awesome. That's why I made that. Okay. So now we want to. Now I want to tell you about the equations of. The integrals of motion that prove that this model is integrable. I'll tell you quick two things that I thought about doing because I thought it might be interesting and they didn't work. The first one is machine learning. Well, maybe it's just because I'm a bad machine learning person, which is true. I don't know how to do it, but there's been a lot of talk about like machine learning equations of motion and trying to find symmetries hidden in these theories. I don't know if these were just too simple, or as we'll see later, if they're just too many symmetries that it was hard for it to find what it was looking for. The other way we initially were studying this model is just to brute force it. Like I said, you can really just generate tons and tons and tons of scattering experiments. So one thing you can just think of doing is, well, let's just guess kind of the possible, do guess and check work really quick. And again, you can find the integrals of motion, but the problems, of course, with the integral of motion is that once you have one, they're hard to disentangle. because the sum of any two gives you a new integral of motion. So really the question is not, okay, are there integrals of motion which tell you that this system is integrable, but are there physically meaningful integrals of motion that give us insight into the model? That's what I'll tell you about now, and the answer about how to what to look for is really to trust the bits, to follow the bits. So I'm going to draw. So what do we have so far? So we have that this dynamics depends on some set of discrete variables. That's A. And it'll prove fruitful to consider the space of all those discrete variables. I'm actually lying a little bit. We're not going to show the whole space because that gets quite large, right? It grows exponentially. But I'll show you some truncated version of that space. And so let's draw this configuration as reference. So we could, for instance, be looking at this configuration of 3 particles in the middle of scattering. Remember here, I call this S01, and I call this, like, say, S30. And those are always set to be -1. So the way we'll solve this model eventually is to go to what we call bit space. And so to generate bit space, you just we'll start with A, the label A going this direction. And we'll figure out what this other direction is later. So you start, and at every position, you draw all the possible choices that SA could take. So for instance, after this first one, which is fixed to be -1, open circles will be -1, closed circles will be +1. So after the first one, we have a particle, which can be either left moving or right moving. And after that, we just fill in all the possibilities. So this next particle, well, could also be +1, -1. But we want to consider all branching options of this string. And so, again, this is not the full space, which is much larger. This is the one that's easier to draw. So I'll just keep.
So should it be a binary tree? You're not drawing a binary tree.
Yeah, that's right. So I'm drawing some truncated version of it. Yeah, so you would think like once I go to this point, then this point, it should be different than going to this point.
Yeah.
Right. Yeah. So I'm not drawing a binary tree. That's what I was trying to say. Is I'm drawing a truncated version. So this is
because it's easier to draw, or because that's a better.
Well, it ends up to be a better tracer of the dynamics. Yeah.
Okay.
And kind of one way to think of that is like in a binary tree, a change at the beginning will affect where I am at the end of the binary tree. But we don't want that in this picture that will be created.
Okay.
That makes sense. Yeah. Maybe it's not super well motivated at the beginning, but you'll see in just 1 second that it's quite a nice space to do things on. Okay, and if I'm to draw all of the positions that all these particles are at, I find that this string configuration gives me a string in bit space. And because this final leg is pinned to be -1, again, here I'm pinned to end at -1. This provides so now let's look at what these equations of motion look like in this space. Actually, it gives a very nice, just looking at it, you can tell what's going to happen next. For instance, if I'm in a configuration like this, where A is in the center of one of these segments that stretches up and to the right, You can see that these two signs are the same, so they cancel. Feels no, it's not changing. Similarly, if I'm in this configuration, and it's not changing. So whatever variable sits here has no time derivative. On the other hand, so that tells me immediately that the only things that can be changing are the ones where I have some kink, right? And I have two possibilities to consider. I either have this possibility, or I have this possibility. Okay, I have, again, this is a minus 1, a plus 1. A minus 1 is minus 1, minus minus 1. So I find that Q dot is minus 2. And so in this configuration, I can only be decreasing, which means that the only kind of non-trivial thing which should happen in this configuration is I start with this variable positive, and it goes negative. So I can only have this sort of change. Likewise here, going through the same calculation, I find I have 1 minus minus 1. So this is 2. So this variable, whatever it is only increasing. So only non-trivial thing that can happen here is that a string configuration like this. Like this. So actually this gives a very kind of fun and intuitive picture about what happens during this scattering. Namely, at early times, you start down along this boundary, and as time increases, you have some sort of crystal melting process as this string walks its way slowly up to the top. And dynamics ends when it reaches the top of this diamond here. That make sense?
So each set configuration is characterized by a set of infinitely conserved charges.
No, so well, this will be it's classical mechanics, so we don't have infinite degrees of freedom. So we'll find.
You can have also in the classical, it's classical integrable, right? So there are classically infinitely many conserved charges.
Yeah, I mean, we'll find that there are, well, there should be proportional. Do you mean, well, you can construct as many as you'd like, but only a couple of, or only a certain number of them are independent, right?
Because the system is a
Yeah,
finite
the system
number of
is
degrees of
finite,
freedom.
exactly.
But the question is whether the conservation of these charges is not enough to determine the way that the configuration evolves.
Well, they will, yeah, they will be, yeah, they will be. That's what we'll say.
So here, I'm a little unclear as to why you've drawn the starting point the way you have, but
Oh, which
The-
starting point?
well,
You
you've
mean
drawn a
like the
particular
left?
configuration.
Yeah, this one? Like this?
Well, you've drawn a line through the middle of
Yeah,
the
which is
code.
this,
That's-
it's
that's-
this configuration. I
And
just
but that's in the
translated
middle
it.
of the scattering
right, yeah.
process. I see.
I just
Okay.
felt like doing that because it was the top and bottom kind of look very simple, right? They just look like those.
Right. And the point is that no matter where you are, you have to go up.
Yes, you have to go up, so you always start down here and you slowly walk your way up.
Okay.
Okay. This picture also tells you something else, which is nice, is whatever point you end on here, you end on for all time. So this is our first integral of motion, we'll call T. How do we describe it? Like, what is it? Well, it's just the number of steps you took up in this graph, right? Looking at this picture, you can see which S, right? So whether you took it up or down, right, depends on whether you after this variable you have a +1 or a -1, but that depends on the previous variable as well, because if I have a -1 here, it means up if the previous one was -1. But if I have a -1 here, it means down if the previous one was +1. So you need to take into account this. And so what you find is that the correct prescription simply the following. This is the first integral of motion, which looks like a Ising Hamiltonian with some classical bits 0 to 1, right? which is kind of our first, first tantalizing hint, but anyways, we'll talk about it later. There's actually another way that is equally as nice to understand this object. If I just undo my dictionary from SA to SI and I plus 1, I can rewrite this variable t as the following. What does this look like? Okay, so if I have particle I minus 1 here, particle I here, particle I plus 1 here, then the SI term contributes to the sum as SI. On the other hand, I have this configuration, then this SI term in the sum contributes as minus SI. Of course, if I have configuration like this or this, the SI term doesn't contribute at all. So another way to understand what this is telling you is it's counting the number of left movers minus the number of right movers computed along the string. That makes sense? So it's comparing the orientation of the string locally to space-time at every point. Okay, but that's just one. We want n at least to explain all these conservation laws. So where do the rest come from? Well, one thing we saw from doing this brute force method that I was mentioning is that, and also kind of conceptually, it makes sense that since the equations of motion are piecewise constant, then it makes sense to look for piecewise linear equations of motion, because that's what that's what the motion of the particles looks like at every moment. So maybe there's some special way to combine them such that you have a quantity which doesn't change. So a good starting point is to look for integrals of motion of the following form, where FA, I'm just thinking of some function of all the signs I have. Okay, take the time derivative of this and we want it to be 0. You get two pieces. Okay, I'm taking a derivative of a bunch of signs. I'm going to get a bunch of delta functions. I don't want those because that's not 0. So the only delta function which is allowed is if this is proportional to delta of 2a. And it turns out that what that means is that instead, FA should really just be the function of, I'll call TA. What do I mean by TA? TA is just the same as this. Well, I'll call it TP here, except you stop the sum before you get to the end. Okay, going back to this picture, TA is just telling you where you are on the height of this graph. And so obviously that's not something which is constant during the motion, right? We're walking up this graph, but it gives you a good repackaging of the dynamics, which is why I wrote this to begin with, right? This direction here is TA. Okay, so that's what you get from the first. Setting this first term to 0. All right, now we want to set the second term to 0. And just using my equations of motion, I get the following equation. I'm going to call this this quantity C. C is 0 for all times. So in particular, the time derivative of C is 0. It's a very trivial statement. But it's actually very useful because time dynamics happens in this picture by a local updating rule, right? From here, I could update to here. Or from here, I could update to here. And C must be 0 on all these configurations. So what that actually gives me is that gives me a recursion relation among these 4 points. And I actually get a recursion relation for every set of 4 points given to me by that equation, by saying that the time derivative of C is 0. And so with this recursion relation, it means if I have these 3, if I know, let me see. What do I want to say here? Okay, so this function f a, right, depends on ta. So what does that mean? It means that everywhere over this graph, right, it's a function over a bunch of discrete variables. So at every point in this graph, fa is just a number. So then what this recursion relation says is that the value of f here is determined by the value of f at these 3 points. That is applied to this whole graph. Of course, to recursion relations, you need to supply boundary conditions so that you can start doing the recursion relations. So if you supply boundary conditions, say along this bottom boundary, then you can fill in what the rest of the FAs are over the whole graph. Furthermore, I want to draw that again, but I don't want to get too dirty. Furthermore, these recursion relations are actually linear. And so I should just, since they're linear, I can just consider the case one at a time where my FA is 0 everywhere except save for like 1 point along the boundary. And then I can add them up later if I find that interesting to do. And what you see kind of thinking about a recursion relation on points collected like this is that if it's 0, if for my function, this function f is 0 everywhere on the boundary except for 1 point, then what this recursion relation says is that it's f everywhere except for along this line. At the end of the day, you find that you have exactly as many integrals of motion, right? This is now an integral of motion. If I satisfy this recursion relation, the time derivative of it is 0. You have exactly as many equations of motion as you have internal diagonals to this bit space. Hopefully that's only very messy. So in this example I drew here, you have 3 left moving ones, and you have 1 right moving one. And actually well, I'll explain those names in a moment why I call them left and right. And you actually get 1 more from the boundary here, because there's a way to satisfy the recursion relation there as well. So actually find 5 constants of motion in a system that only has 3 particles. This is actually more than we bargained for. We were only looking for 3 equations of motions if we had 3 particles, but we got 5 instead. And this pattern actually continues to n particles. For n particles, you find, using this procedure, that the number of integrals of motion you get is 2 n minus 1. And this goes by a fancy name, which is maximally super integral. That means we just did a very good job. We found even so many of the system actually is almost free. Almost nothing is changing in the system, even though it looks like, it looks like something's happening.
What are the crucial ingredients? Well, suppose that you take this original Hamiltonian that you have and you modify into a square of qi minus qi qi minus qi plus 1, roll it linearly. What if you take it to be squared or square root or other functions? Would it, this structure of integrability or super integrability that you described will be dramatically modified, or it would be?
I mean, my expectation is that it will disappear. So kind of my understanding of where this is coming from is exactly because like, this sort of simplification is happening. Is that the equations of motion for the momenta and the particle differences are looking the same. There's something that happens there. So generically, if you change the potential, that will change that. And for instance, instead of changing the potential, if you change the kinetic energy, we saw explicitly with some computer simulations is that it's not integrable.
It's a property of this particular model.
Yeah, exactly. That's very interesting.
Also, what about the dynamics of the model? So, I mean, do you form here bound states of K of these adjoint fermions? I mean,
Well, so
or bound set at all?
no. Here we only have scattering.
I know, but I mean, on top of that, what would be the spectrum of theory?
Well, yeah, I mean, there's. Well, you'd expect there to be also some closed, like to be some non-trivial spectrum of closed strings, if that's what you mean in this background. But we've taken the large n limit so that they don't interact, so we can study them we can study this system on its own without talking about closed string spectrum.
Well, I'm wondering whether if you do the scattering, you will form bound state of 2 adjoints, 3 adjoints, 7 adjoints. They can
That would live on the string, or do you mean it would like
Yeah.
disconnect and go into the bulk?
So on the string.
Yeah, I don't. Well,
You just argued that can't happen.
well, I think he's asking something different, which is. Do you mean in the QFT that we started with, whether or not you can get bound states that live on the string? Yeah, I'm not sure that, like, as I said, we threw away contact terms or anything that doesn't grow with distance. So I'm not sure I could rule out the possibility that one of those terms would give rise to something like that. But I don't know off the top of my head. Okay, so we got this maximally super integrable model. And I said that this is almost free. And actually you can kind of formalize what that means. If you just label all your diagonals starting I1, and we'll just call this right. I2, blah, 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 blah. Here the same, starting with 1. I2, blah, 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 blah. What you find is that the odd diagonals asymptotically give you the particle positions, and the even diagonals asymptotically give you the difference in particle positions, if they're both, say, right movers. So what this means is that the scattering in this model looks something like this. You have some clump of right movers coming in. You have some other clump of left movers. And after their interaction, they stay exactly the same width. And the only thing that can happen is that there can be some time delay associated with the scattering process. Actually, this is yeah. So yeah, this is not something I think I noticed, the first time looking at the dynamics, is that not only are the momenta all conserved, but also the particle distance among left movers and right movers. So this is the manifestation of all this super integrability. And you can actually go further. You can promote this I odd, not only asymptotically to be some momentum, but actually if you throw caution to the wind, call this a momentum, call the even ones particle distances. Then with one more ingredient, you can get a set of positions and momenta, and you find that on every sector on which they're defined, that these coordinates are canonically conjugate. exactly in this sector, you can also rewrite the Hamiltonian of your theory. So it looks like the following. This looks like a collection of free particles. So this is the manifestation of the maximally superintegrable. It's really almost looking like a collection of free particles. Of course, in this picture, there was some interaction and there is some time delay. And you can calculate that using all this machinery that we developed. And what you find is that the right moving particles are delayed due to the total left moving momentum. The left moving particles are delayed due to the total right moving momentum. Now, this is something we were kind of expecting. I won't go into this because we're well, time's up and etc. But this is something we were expecting to find, and actually matches the scattering that happens in shock waves and gravity, and also to something that Eva mentioned at colloquium last week, which is this TT bar deformation. So this is something that we were expecting to find. And what we've been doing for the last year is quantizing this model. And I'll tell you that in 2 seconds. It's been difficult. Quantum mechanics, it turns out, is not so simple. And also it depends very much what you quantize, right? And just one of the key insights that we had to continue this story to quantum mechanics is that instead of imposing this sort of quantum mechanics quantization relation, that it actually makes sense to instead quantize these new coordinates that we found. And view the interacting coordinates as functions, free coordinates. Yeah, one kind of funny thing that didn't come out of this is that we didn't see an upgrade to this bit space picture. It kind of almost feels quantum, right? Feels like maybe there's a way to upgrade that so it just becomes quantum mechanical, but it's kind of interesting. This picture disappears. But anyways, yeah, so thank you.
More questions for Jack?
You mentioned that the variables capital Q and capital P are defined in sectors. Right?
Yeah, that's right.
So they're not globally defined. But you
Right, and you can understand that here just because only some of the diagonals intersect any given.
Sure. But you say that for the quantum mechanics, you impose the permutation relation on these.
Yes.
So you have like different sectors. of
Yeah,
the
that's
field,
right, yeah.
And on each sector, you impose your.
Yeah, that's right. And another way to understand that is like you choose this quantization, you lose all these sectors.
Okay.
Because you're dividing
Oh yes.
space by how many left movers, right movers you have, but
And also, I mean, this capital Q remind probably are the action angle variable. Usually, when you deal with quantum mechanics, you should bring your system to sort of action angle.
Well,
you keep things take a look and then quantize that.
that's one nice thing to do, but
Yeah,
I wouldn't say
it's
you're,
much nicer.
yeah, I
to
wouldn't
do
say
it
you're
that
forced to
way.
do that.
No, you're not.
Right.
But that's the nice thing.
But these are globally defined action angle.
Yeah,
variables.
Yeah,
that's what
that's
my question.
exactly-
So usually you have this globally defined action angle variable and you quantize this, but in this case, you need to restrict the sectors.
Yeah, so there's restrictions on sectors. There's also the fact that these PI, whether they're left moving or right moving, are actually constrained. So it's not a canonical quantization, actually. So there's been many confusions in that story for us, but I think we got it cleared up mostly at this point.
You added the fermions in the adjoint.
Yes.
Nevertheless, you do the quantization as if they are scalars. You can also add scalars in the adjoint.
That's right.
Would the picture be different?
I'm not sure if at this level it would be different. I know they are different. And there's mostly people study the addition of fermions because I think that gets you closer to a string theory picture. But I know people also
But
do
in
study the
90s,
scalars.
You mentioned at the beginning, people also study the scalars.
Yeah, that's right. Yeah, people do, but But I think the I forget the exact reason, but I think the fermions are usually more interesting.
Anything else? All right, thanks, Art.
Yeah, thank you.
Yeah, but I don't know. Yeah.
Doesn't work, but kind of-
Yeah, we're